Hi everybody, I hope this video finds you well. In today's video, we're going to be moving into section 7.5 from your textbook, which talks about strategies for integration. This is sort of an interesting section because in this section, we're not going to introduce any sort of new concepts or techniques for integrating functions. Instead, we're just going to try to summarize and talk a little bit about how you would pick out an appropriate strategy for a sort of random integral that you need to do or for an antiderivative that you need to find. If you think about it, in each section, choosing the sort of integration technique was relatively easy because each section introduced one technique and we sort of knew if we were doing something from that section, then we should probably try to use that technique. In general, if you're just performing some antiderivative or trying to compute some integral, you're not going to know ahead of time what is going to be a good sort of technique. So our goal in this sort of video is to sort of summarize the techniques that we've discussed so far, talk about how you strategize to choose an appropriate technique or combination of techniques, and then look at some examples sort of using that strategy. So the first comment that I'd like to make is, hopefully at this point, with all the sort of integration that you did in your Calc 1 class, plus all the integration we've been doing since we started Chapter 7, you guys have seen that integration is a very different mathematical process from differentiation. Differentiation is very, very formulaic. For differentiation, if you apply the right rule or combination of rules in the right order, you know you're going to always be able to determine the derivative of a given function. For integration, that's definitely not the case. There are functions that do not have easy closed form integrals, meaning that when we try to actually take their antiderivative, we can't come up with a simple function that is actually their antiderivative. There are simple functions that require advanced techniques to integrate. We saw that we had to get all the way into integration by parts before we were ready to actually go ahead and integrate something as simple as ln x. So integration is really a creative process. When you're given an integral, you have to try to determine, can I integrate this directly? Do I need to use a technique to manipulate the integrand into a different sort of expression that I can work with more easily? Integration really is a mixture of trial and error, intuition, and also an understanding of the different techniques that we have introduced. So it's very important to recognize that when you look at an integral, it's not like a derivative where you're just going to immediately know what you need to do. You really need to sort of play around with it and sort of think about what is a good path, work on that path a little bit, and then see where it leads you. And that means that if you choose a path that doesn't work so well, there's nothing wrong with trying something and realizing it's not really getting you anywhere useful, and then sort of backing up and trying something else. So, in that note, what are the sort of techniques that we've discussed? Well, all the major integration techniques that we've covered in our class, as well as what you saw in your Calculus 1 class, namely U substitution, they're all attempts to change the integrand into a simpler expression that hopefully we can then directly integrate. That's what everything is about. There's no sort of tricks to integrating. Instead, there's tricks to changing the integrand into something that we already know the antiderivative of. So what are the sort of major techniques that we've covered? Well, I would basically classify that there are four major techniques that we've discussed for changing the integrand into an expression that hopefully we can directly integrate. Those techniques are U substitution, integration by parts, trigonometric substitution, and partial fractions. You'll notice that one of the sections that we covered, the section on trigonometric integrals, which was section 7.2, is not listed as a technique. And that doesn't mean that it's not important. Trigonometric integrals was more an exploration of how to take that very specific type of integral and modify it using trigonometric identities to sort of simplify the integrand into something we can directly integrate. That's definitely very important, but I wouldn't really consider it a general technique since it really only applies to expressions that are products of trigonometric functions. Now, why is that so important? I mean, why do we see products of trigonometric functions? I mean, are there just lots of products of trigonometric functions floating around out there? Well, there are actually some models, some real-life models that are based on trigonometric products. So they do have some just direct application, but the really important thing is that this technique, trigonometric substitution, always after the substitution results in a trigonometric integral. So having a good understanding of how to work with trigonometric integrals from that section 7.2 is so important because not only do we sometimes just see those integrals in themselves, but trigonometric substitution is always going to lead there. So we want to make sure we know what to do once we get there. Okay, so let's talk a little bit about strategizing how to choose a technique. So, U substitution. As I think I've mentioned many times, U substitution is often used when the integrand involves a composition of functions. So if you see a function inside of another function, that is a good sign that you might want to try U substitution. What do we mean composition or function inside a function? We mean things like if you see sine of the square root of x. That square root of x is a function, but it's been plugged in to sine of x. You see something like e to the x squared. The x squared is a function, but it's been placed into the exponential e to the x. So anytime you see a function inside of another function, that's a composition, and you want to try to attempt to use U substitution. When attempting to use U substitution, remember the U, what you're going to actually substitute for, is that inside function in the composition. Sometimes the U substitution is going to run really smoothly because the du, the sort of catalyst for the substitution, is going to be easily able to be found in your integral. Sometimes you're going to have to mess around a little bit with solving for the dx in terms of du, working with the substitution. There's clean substitution, there's imperfect substitutions. You just got to sort of play around with it. But composition is a good tip-off that U substitution might be a good choice. All right. Second technique, which is really the first technique we introduced specifically in our class, integration by parts. Integration by parts, as we know, it's reversing the product rule for derivatives, so it's often used when the integrand involves a product, two functions multiplied together. Keep in mind, though, that a quotient of two functions can be rewritten as a product, especially if you make use of changing exponents into negative exponents. You see something like natural log of x divided by x squared. Okay, that's a quotient, but if you think about that as natural log of x times x to the minus 2, now it's a product. So integrands involving products or simple quotients that can be rewritten as products, integration by parts is a good choice. A little bit less common, but still happens, is integration can be by parts can be used to integrate a single function when we do not just have a well-known antiderivative. That's actually the trick that we used for ln x. We also saw that it worked for arctan of x. There are other functions out there that sometimes if you feel like there's not really a composition going on and you just don't know the direct antiderivative, you can always try integration by parts and work from there. Trigonometric substitution. Trigonometric substitution, very important technique, but it has a very specific type of integrand that we often use it for. It usually is involved when we have a radical of a term of the form a squared minus x squared minus a squared, or a squared plus x squared, right? Those types of expressions, because they're in that a squared minus x squared minus a squared, or a squared plus x squared, they directly allow you to create a Pythagorean identity if you do a trigonometric substitution. So definitely be on the lookout for these. If you see those types of expressions in your integrand, then trigonometric substitution might be a good idea. It often does also involve a radical, meaning like a square root or a 3/2 power or a 5/2 power, something like that. But this is probably the easier tip-off to sort of realize, okay, maybe I want to use trigonometric substitution. Remember, though, in general, we also, when we talked about trigonometric substitution, even if you don't see this exactly, if you just see a quadratic term, you can always complete the square and put the quadratic into one of these forms. So maybe you see something like x squared plus 2x plus 1. Well, x squared plus 2x plus 1 doesn't look like this, but you can rewrite x squared plus 2x plus 1 as x plus 1 squared plus 0 squared, and then maybe you can work from there, right? So you can always go ahead and complete the square and rewrite something into this format. The last sort of technique, the one we developed in the previous section, section 7.4, is partial fractions. Partial fractions is maybe perhaps the easiest one to identify because it has one specific type of function that it applies to. Rational functions. What's a rational function? Rational function is defined as a polynomial divided by a polynomial. So if you see a polynomial divided by a polynomial, then you know partial fractions is a good idea. Partial fractions technically only applies when the degree of the numerator is less than the degree of the denominator. Remember, if the degree of the numerator is not less than the degree of the denominator, then you can simply do polynomial long division, get something where the degree of the numerator is smaller than the degree of the denominator, and then use partial fractions. So anytime you see a rational function, you can think, I can do this through partial fractions. Does that mean that partial fractions is always ideal? Not necessarily. It's probably one of the most algebraically intensive methods, since you have to determine those constants and everything like that. But if you ever see a rational function and you're stuck with how to integrate it, know that partial fractions will do it for you. Might not be the cleanest way, but it will work as long as your function is rational. Finally, as sort of not a general technique, but just something to think about, if you're convinced that none of the above techniques really seem to help, or you try the above techniques and they don't seem to be getting you anywhere, then the last sort of strategy we have is to try algebraic manipulation, meaning that instead of trying to use these integration techniques to change the integrand, we actually just try to manipulate the integrand algebraically. Usually, this comes in the form of like using a trig ID, so changing a sign that is in the denominator into a cosecant, or seeing a tangent and splitting it as sine over cosine. Sometimes you can rewrite products as quotients and quotients as products, so that might help. And sometimes, as we know, one very common algebraic manipulation is the use of a conjugate. If you see something that's like an a minus b format, you can always multiply by a plus b over a plus b, build those difference of two squares, and maybe that'll simplify things. So if you feel like none of the techniques are really helping you, then you can always try to manipulate things algebraically. Okay, so this is just sort of a brief discussion of the different strategies. I'm going to do a couple examples now, and we're going to talk about the strategy before we jump in to do them. So each of these examples has really got two components to it. One is sort of the logic that lets us arrive at the choice of the correct technique or combination of techniques. And then, of course, we'll actually also solve each of these. To be honest, though, I'll walk you guys through these examples because I think that it's good to see a few. But the only way to be truly comfortable with strategizing for integration techniques is to just try as many examples as you can. If you look at the suggested exercises from the textbook for 7.5, those are good ones to do because the integrals in section 7.5 are all mixed together. So all the techniques are in there and you can practice everything. There will also be a separate document posted on your guys' Canvas file section with some more integrals just to practice. You have solutions to it just to really practice this sort of strategizing of integration. Okay, so let's get into our examples here. So we're going to try to do this guy here first. So we want to try to determine the following indefinite integral. We've got the integral of 4x cubed minus 4x squared plus 9x minus 10 divided by 2x minus 1 squared dx. So what do we notice about this? Well, the first thing we can probably notice is that this is rational. Right? This is a polynomial up top. This is a polynomial on the bottom. So if nothing else sort of works, we got partial fractions. If we also look at this, we could think about maybe we can get away with like u subbing for the denominator, but that doesn't really seem to make a lot of sense because if we did something like u equals 2x minus 1, then the du would be like 2dx. I suppose we could try to factor a 2 out of this, but then we get ugly fractions there. And we would also have to rewrite everything in the numerator in terms of u equals 2x minus 1, which sounds really, really messy. So doesn't really seem like there's much else to do. So we probably want to try to go down this rational partial fractions route, especially since we know that'll work. Now, for partial fractions, the degree of the denominator has to be larger than the degree of the numerator. Degree of the numerator here is 3, and the degree of the denominator, if we multiplied it out, would be 2. So we can't use partial fractions right away. So we want to make a note here. The degree of the numerator is greater than or equal to the degree of the denominator. So we need to do division first. So it would probably help to have this guy actually written out as a polynomial. So 2x minus 1 squared is really 4x squared minus 4x plus 1. So let's go ahead and do our long division. 4x squared minus 4x plus 1 divided into 4x cubed minus 4x squared plus 9x minus 10. Looks like we should get an x there, and then minus 4x cubed minus 4x squared, and then plus x. And if we subtract, then those are going to cancel, those are going to cancel, and it looks like we're going to get 8x minus 10. Notice that the degree here is 2, and this is degree 1, so you cannot divide this in here because you can't divide something that has a larger degree into something smaller. So this is just going to become our remainder. But notice that's not going to be a problem because we're going to have this divided by 4x squared minus 4x plus 1, which will be in appropriate partial fractions form. So after our division, we know that we have the integral of x plus 8x minus 10 over 4x squared minus 4x plus 1 dx. So, in other words, this messy expression is equivalent to this simpler one. Now, certainly integrating this x is going to be nice and easy, so we just need to focus on this. So, let's go ahead and do that first before we actually do any integrating. So, we'll go ahead and do this as partial fractions now. Because of the fact that we already know what this factors as, things are a little bit easier. We have 8x minus 10 over 4x squared minus 4x plus 1. And that needs to be the same as 8x minus 10 over 2x minus 1 squared. And we have a repeated linear factor here. So since it's linear, the numerators are going to be constant, so a over 2x minus 1. But then since it's repeated, we'll have a second one, b over 2x minus 1 squared. Remember that the number of constants that you need to solve for always matches the degree of the denominator. Degree 2, we've got 2 constants that we need to solve for. Easiest way to do this now is, of course, to go ahead and multiply by the LCD, which of course is just this denominator here. So we get 8x minus 10, looks like a times 2x minus 1 plus b. And if we multiply that out, we get 8x minus 10. And instead of multiplying out, if you want, you could get one of these for free by plugging in the root here. So let's just go ahead and do that. Let's let x equal 1/2. Why are we choosing 1/2? Because that's the root for this linear factor, and it'll cause that to be 0. On this side, it looks like we'll get 4 minus 10, which is going to be negative 6, is going to be 0, and then b. So there's one of our constants. And since there's only one factor, there's only one easy value to choose. Otherwise, let's go ahead and just multiply this out. I'll sort of do this over here. We have 8x minus 10 is equal to 2ax minus a plus b. We could set the minus 10 equal to minus a plus b, but it is probably even easier just to match up these like terms, the 8 and the 2a. So we get 8 equals 2a, and we get a equals 4. So there's our 2 constants there. Okay, so let's go ahead and move on to our next page and actually rewrite this. So at this point, we know that this is the integral of x. And then instead of this 8x minus 10 over 4x squared minus 4x plus 1, we can replace it with 4 over 2x minus 1 and minus 6 over 2x minus 1 squared. So we get 4 over 2x minus 1 plus minus 6 over 2x minus 1 squared dx. And now we should be able to go ahead and integrate each piece. So integral of the first one is going to be 1/2 x squared. This piece here technically should be a u sub. It would be u equals 2x minus 1. du is going to be 2dx. So that means we're going to get an extra factor of 1/2 when we actually do the substitution. So you should be able to sort of do that in your head because this is a linear substitution and the derivative is 2. So since we're doing the antiderivative, we get a factor of 1/2. So this is going to be plus 2 ln absolute value 2x minus 1. This thing, if you think about it as substituted, is going to be over u squared. And that means it's really going to be u to the minus 2. So when we integrate this, we'll get a factor of 1/2 from the linear substitution. So this is going to reduce to a 3. And the new exponent is going to be negative 1. We divide by that negative 1, and we should get plus 3, 2x minus 1 to the minus 1. We've finished all our integrals, plus c. Now, when we jumped from here to here and from here to here, both of those were u substitutions. There's nothing wrong with going ahead and just writing out those u substitutions fully. But again, since linear substitutions show up so frequently, it's nice to be able to get sort of used to doing them in your head and just being able to make the jump here. So even though it was a messy rational function, we were able to determine the antiderivative and notice that there wasn't much we really had to strategize because since it was rational, we knew partial fractions was going to be a good way to go. All right, let's take a look at another one. So we are going to try to determine this indefinite integral, e to the square root of x dx. Now, when we look at this, sometimes these ones, which are sort of the simpler expressions, I mean, this is not nearly as messy as the previous one, can be a little bit harder because since it's so simple, there's not much that we can really see is going on. So we can rule out some things. We see a radical, but we don't see anything like x squared minus a squared in there. So, probably not a good idea to do trigonometric substitution. Also doesn't really make a lot of sense to do trigonometric substitution. We've never talked about trigonometric substitution with an exponential. It's not a rational function, so we shouldn't be worried about partial fractions. This is not a product. It's e to the power of square root of x. We could maybe try integration by parts because, like we said, sometimes integration by parts can work with a single function, but usually it's better with products, and this is not a product. But this is e to the square root of x. And if you think about that, e to the square root of x is a composition. So since we have a composition here, the technique we probably want to try is u sub. Doesn't mean that it's going to work, but it's a good place to sort of start. So what should we u sub for? Well, the inside, which is the function that's been plugged into the other, so we would say square root of x. And then, we don't see a du floating around, so we're just going to have to sort of see what happens. Du here is going to be the derivative of square root of x, which if we think about it, that's x to the 1/2, so we get a factor of 1/2. Then x to the 1/2 minus 1, which is negative 1/2, so I guess 1 over square root of x, and then dx there. Now, none of this stuff shows up, so let's just manually solve for dx, right, by bringing this stuff over onto the other side. So it looks like we get 2 root x du is equal to dx. So let's plug that stuff in. We get integral e to the u. So that's substituting that just directly in there. And instead of dx, we're going to have all this stuff. So we're going to have 2 root x du. Now, this is not an appropriate form because we've got u and x and du, right? Since we are working du, everything needs to be in terms of u. But notice that u is equal to root x, so we can replace that right there. So we can actually make this e to the u, 2 times u du. And if you rewrite that, you can sort of view that as 2u e to the u du. Now, at this point, we did our composition. It's sort of nice because we don't have a square root anymore, so that is better. But now we need to reanalyze. This is a whole new integral, so we can think about all our techniques again. The first thing that should jump out to you is that now this is a product, and it's a product of relatively simple functions, 2u and e to the u. Obviously, the 2 could go anywhere. We could even stick it outside, but I'm just going to carry it along here. It's a product. It's a product of 2u and e to the u. So let's try integration by parts. So we've got a product. So let's try integration by parts. Now, of course, we usually would use u and dv, but since u is being used, we'll say w and dv. Remember that whatever you choose for w, you're going to differentiate, which should never be a problem. And whatever you choose for dv, you're going to have to integrate, which may or may not be a problem. Now, 2u, certainly know how to differentiate that. 2u, certainly also know how to integrate. Same thing for e to the u, certainly know how to differentiate, certainly know how to integrate. So, since we know that either thing can be placed in either spot, the real question is which is going to simplify more under differentiation? Well, if we put the 2u here, when we differentiate it, it's just going to become a 2. That sounds really good. Whereas if we put the e to the u here, when we differentiate it, it's just going to be e to the u. It's not going to change anything. So it seems like it'd be a good choice to put this here and this guy over here. So let's put the 2u here and the e to the u du here. Differentiate, we get 2 du. Integrate here, we get e to the u. And then we do wv, so we get 2u e to the u minus the integral of v dw. So 2 e to the u du. Still have an integral to do, but it's a nice and easy one. Integral of 2 e to the u. You can just bring that 2 outside if you want, and then integrate the e to the u as e to the u. So we get 2u e to the u minus e to the u, finished all our integrals, plus c. Then we can look back and remember that our u was actually square root of x. So we pop that in there. We get 2 root x, e to the root x minus e to the root x plus c. So there we go. We've actually managed to figure out the antiderivative. Key thing here was to recognize that we had a composition. The composition was told us to use a u sub. We played around with the u sub. It wasn't perfect, right? We couldn't find the du in there. There was no 1/2 1 over root x to just plug in and just change into a du. So we had to solve for dx in terms of x and du, plug that in, and then converted this new square root of u, or square root of x, into a u, so that everything was in terms of u. And then the really crucial thing is that this was now a new integral. So we had to redo our whole strategizing moment. We realized it was a product, so we went ahead and did integration by parts. All right, let's go ahead and take a look at our next one. So we want to try to determine this indefinite integral, 1 over the square root of 3x plus 8 minus secant squared 5x dx. Why is this one that we're going to take some time to talk about here? Because this is a great example of realizing when you don't really have much to do. This is actually an integral. We can go ahead and directly just integrate. Because even though these are messy sort of expressions, both substitutions that you're seeing in here, that 3x plus 8 that is sort of inside the square root, and that 5x that is inside the secant squared, are both linear substitutions. So they're the easiest substitutions to do. They always work because whenever you do u equals ax plus b, the du is always just going to be a dx, meaning you just always get a 1 over a factor. So you can always do linear substitutions. Other substitutions, you have to actually see if they're actually doable by solving for the du or the dx, going from there and working out and seeing whether or not you can complete the substitution. But linear ones, you're always able to do. So let's go ahead and rewrite this a little bit. Let's recognize that this is 3x plus 8 to the minus 1/2 minus secant squared 5x dx. Okay, for this, we know we can use power rule. The new power is going to become a 1/2 power. We're going to have 3x plus 8. But we have to divide by the new exponent. Dividing by 1/2 is a factor of 2. And then we have to divide by the derivative in here, which is going to be that 3. So we're going to get 2/3. Would that work if in here it was x squared plus 8? Could we just divide by 2x? No. Absolutely not, right? If it wasn't a linear substitution, you can't just use this trick of doing 1 over the derivative, right? It's all based on it being a linear substitution. If you want to check this, though, feel free to just do this integral separately with u equals 3x plus 8, and you should be able to get right to here. Same thing over here. We know how to integrate secant squared. We know that that's just tangent. So we're going to get minus tangent 5x. But since the derivative of the inside is 5, we'll get a 1/5 in front of that. And we've completed everything plus c. So why are we talking about this one? Again, just so that you guys can always sort of remember, not everything requires a technique. Sometimes, right, we have expressions that maybe look complicated, but we know how to actually just directly integrate them. So be on the lookout for things you do know how to integrate. That secant squared might look messy. I mean, that's a secant and then being applied with the square function, but actually we know secant squared is just the derivative of tangent, so it actually makes things nice and easy. All right, let's go ahead and take a look at another one. All right, we're going to try to determine this indefinite integral, 1 over 1 minus cosine x. Okay, now the first thing that should jump out to us is that this is a trigonometric integral. Unfortunately, if you think back to what we covered in 7.2, when we talked about trigonometric integrals, we talked about products of sines and cosines. This, unfortunately, is not a product of a sine and cosine. It's a quotient of a constant and a cosine. And we also talked about products of secants and tangents. Well, we could try to rewrite this, right? We could try to say, well, let's try to get the cosine out. We could multiply the top and bottom by, say, secant. And if we did that, we get like secant x over secant x minus 1. And notice that that wouldn't solve the problem of there sort of being two terms in the denominator. So trying to flip over the cosine is going to be pretty challenging here. We could try a u substitution. I mean, technically, 1 divided by something is a composition. So you could think about maybe 1 minus cosine x, and then your du would be sine x dx. Now, we'd be suspicious here because there are no sines around. I guess we could swing that over and get that dx is 1 over sine x du. But then if you think about ahead, you plug that in, you're going to have to be able to think of sine of x in terms of 1 minus cosine x. That would be easy if it was cosine squared and sine squared, but not so easy when it's sine and cosine. So you can try those methods, but unfortunately you're going to see that everything's just going to dead end there. Instead, we already sort of just mentioned, just in the sort of brief description there, what would make things nicer. It would make this a lot nicer here if this was 1 minus cosine squared, because then Pythagorean identities would work. Trig functions always look a lot better when you have squares in them. So can we make a cosine squared here? Well, this is 1 minus cosine x. What happens if we multiply by its conjugate, 1 plus cosine x? So let's see what happens there. So we're going to take 1 minus cosine x, 1 plus cosine x, over 1 plus cosine x. Now, this might seem sort of weird, but again, remember, it is based on the logic that working with those trigonometric functions would be easier if we had a cosine squared, and this multiplication is going to make it really nice and easy, because here we're using a minus b, here we're using a plus b. The conjugate guarantees there'll be no cross terms, so everything's either going to be a constant or a cosine squared. So if we do that, we get 1 plus cosine x up top, and in the denominator, we get 1 minus cosine squared. Now, the whole idea was that 1 minus cosine squared we might be able to manipulate, and we can. We can write that as 1 plus cosine x over sine squared. Now, that might not seem like it's made things a lot better, but it actually has. Because if you look at this, this is a single term denominator, meaning you can split this fraction into two pieces now. Can't split apart denominators, right? We couldn't split this guy up in terms of, because it was the denominator. That's not 1 over 1 minus 1 over cosine x, right? That's completely wrong. Fractions don't work like that. But certainly you can split up numerators if you have a single denominator. So we have 1 over sine squared plus cosine x over sine squared. Now, these are very simple quotients. These we probably can rewrite using some trig IDs. 1 over sine squared, well, we know that. That's just called cosecant squared. And this, well, if we think about it, we have a cosine x over sine x. And then I guess we have an extra factor of sine. This is cotangent, and this is cosecant. So we can actually rewrite this as cotangent x, cosecant x. Now, you might say, okay, why do I want to rewrite as those things? Well, both of these, as we know, are actually derivatives of trigonometric functions. Cosecant squared is the derivative, except it's off by a negative sign, of cotangent. And cotangent x, cosecant x, again, off by a negative sign, is the derivative of cosecant. Just like how the derivative of tangent is secant squared and the derivative of secant is tangent secant. So by making these, we can now just directly integrate. This is going to be negative cotangent x, because again, they should have their negative signs, and then minus cosecant x plus c. So the whole thing here, and this is why we say integration is sort of intuition-based, we have to sort of know what are forms that are good. We know a form of something like cosecant squared. That's something we like because it's a derivative of a function we know. Cotangent cosecant, that's something we like because it's a derivative of something we know. So you sort of have to know what things are good to get to, and then as you're doing those manipulations, sort of realize, I can get to a form like that, then I can just go ahead and directly integrate. All right, let's go ahead and take a look at another one. So we've got another one sort of involving trigonometric functions, right? We've got this sine to the fourth over cosecant, secant cubed. Now, again, trigonometric integrals, we did that section. We said we like products of sines and cosines, products of secants and tangents. This is a quotient, and it's got sine, cosecant, and secant in it. But as we know, there's lots of trig IDs that let us move things from the numerator to the denominator, denominator to the numerator. So let's rewrite this as a product, because that's what we spent our time working on. So if I flip this cosecant up, it should be sine to the fifth over secant cubed. And then if I bring this secant cubed up, right, secant is 1 over cosine, so 1 over secant must be cosine. So we can get this as sine to the fifth cosine cubed x dx, just by a little bit of trig sort of manipulation. Now this is a form we like. It's a product of sine and cosine. Also, we've got odd exponents. We only need one odd exponent. We actually have two odd exponents here. So let's choose the smaller one, because we know we're going to have to convert whatever remains when we do this. So let's go ahead and choose this one. So we're going to choose smallest odd exponent. All right, this is actually what we detailed in that first part of section 7.2. We said products of sines and cosines. If there's an odd exponent, you can save one factor from that odd exponent, convert the rest using Pythagorean identity, and then do u substitution. Why am I choosing the cosine cubed rather than the sine to the fifth? Well, if I choose the sine to the fifth, I can save a sine, which will work perfectly, but then I'll have to convert sine to the fourth using Pythagorean identities, which means I'll have to use two Pythagorean identities. Here, if I save a cosine, things will be a bit simpler. So we're going to rewrite this: sine to the fifth cos squared cosine x dx. I recommend doing something to remind yourself that this now is untouchable. We're saving that for a u substitution. U equals sine of x, du equals cosine x dx. Now we would like to convert this, which we can do pretty easily. Sine to the fifth, 1 minus sine squared, cosine x dx. Again, we're not going to touch this. We can go ahead and multiply this out so that everything is in terms of sine. So we get sine to the fifth minus sine to the seventh, all times cosine x dx. And then we can go ahead and do our u substitution now. U equals sine of x. Du is cosine x dx. So if we go ahead and pop that in, we get u to the fifth minus u to the seventh, and then we have our du at the end there. Now we can integrate power rule nice and easy. 1/6 u to the sixth minus 1/8 u to the eighth plus c, since we finished all our integrals. And then simply undo the substitution, popping that back in there. We get 1/6 sine to the sixth minus 1/8 sine to the eighth of x plus c. And there we go. We went ahead and we managed to do this antiderivative. Even though the initial starting expression was something we never really talked about, it was a quotient of sines, cosecants, and secants. We were able to rewrite it as a product of sines and cosines, something we were much more comfortable with. We reminded ourselves of that general approach and was able to get a nice antiderivative. Okay, well, let's go ahead and take a look at one last example that puts several techniques together. And sort of, again, just reminds you that every time you use a technique, you sort of want to reset and sort of work from there. Okay. So we've got a sort of messy one here. We've got the integral of 1 over x times 1 minus ln x squared, all raised to the 5/2. So we've got a lot going on here. We have an ln x inside a square. Then we have 1 minus that, all inside a 5/2 exponent. Then that's times x, and then that's all in the quotient, or in the denominator of 1 over that stuff. So there's a ton of stuff here. So where did it sort of start from? Well, what you probably want to look at is find the most sort of internal thing, especially when you have all these layers in here, and you can sort of see that we have that ln x squared. We've got to do something about that because that's a composition. It's actually several layers of composition. We have an ln x that's ending squared, and then 1 minus that is all to the 5/2. We've got lots of compositions, but let's start with the innermost. Let's try to do a u substitution. Let's do u equals ln x. Right? Just so that we can start sort of working from the inside out. Now, I'm pretty confident about this because if we think about it, du is going to be 1 over x dx. And notice we have 1 over x dx. So anytime you see one of these, which I would call a perfect substitution, it's probably a good idea to do it. Du 1 over x dx. Sorry, maybe I should just say a little bit more. What do I mean by perfect substitution? Well, if you go back to the other one we did here, this is something where I would sort of say this is a imperfect substitution, right? We picked u equals root x because of its composition, but there was no sign of its derivative. So we just sort of had to say, okay, well, let's see what happens if I play around with this, solve for the dx, plug it in, and then hopefully I can write everything in terms of u. It's an imperfect substitution. We didn't know that we'd be able to get everything cleanly in terms of u until we did it. In the one we're working on right now, though, I mean, it is clear that if we do u equals ln x, the derivative is 1 over x dx, and we have that factor right there. So we know at least this step of the substitution is going to work fine. So I'm going to go ahead and, okay, so circle this here, and that dx is going to be used up in that substitution. So let's go ahead and look at that. It's going to be 1 over 1 minus instead of having ln x in there, we're going to have u squared, and then all of that is going to be in parentheses to the 5/2. And then we're just going to have du. So that substitution has done two major things for us. One is that instead of having that double composition, that ln x squared inside the 5/2, well, now we just have 1 minus u squared. Still to the 5/2, so we still have some messiness. But it also got rid of that 1 over x that was out there. So this is a much simpler expression. Now, we want to reset and think about this. How should we approach this? Well, we see this 1 minus u squared. That sort of reminds us of trigonometric substitution. And we can go a little bit further if you want to help yourself sort of visualize it. View this as 1 minus u to the squared to the 1/2, and then all raised to the 5th power. I mean, that's what that 5/2 exponent is doing. So you can see that this, if we wrote it as a radical, is radical 1 minus u squared. So we have a radical of a squared minus u squared. So this is a trig sub here. So we're going to do this as trig sub. Since it's 1 minus something squared, our trig sub should be in terms of sine. So we're going to let u equal sine theta. That means the du is going to be cosine theta d theta. So let's throw all that stuff in there. 1 over 1 minus sine squared theta, all to the 1/2, all to the 5th, cosine theta d theta. Now, standard procedure for trig sub, we chose this to build a Pythagorean identity. Let's plug that in. 1 over cosine squared to the 1/2 to the 5th, cosine theta d theta. Then the 1/2 will cancel out with the square, and we're going to end up with cosine to the 5th in our denominator. So 1 over cosine to the 5th theta, cosine theta d theta. Okay, see an easy simplification right away, right? We can go ahead and cancel a cosine. So we can bring this all the way back up here. And we should have integral 1 over cosine to the 4th theta d theta. And again, that comes from just canceling cosine with that cosine to the 5th. Okay, now we've done another substitution, so we got to sort of reset and think about this. Again, we like products of sines and cosines. This is a quotient of a cosine, and we like products of secants and tangents. Well, luckily, denominator, cosine in the denominator can be thought about secant in the numerator. So this is secant to the 4th d theta. This is great. We said that when you're working with secants and tangents, you're wanting even secants or odd tangents. So this is good. Even secant, right? We said save secant squared, convert rest to tangent. So we're going to save a secant squared, then convert the rest into tangent and do u equals tangent. So we're going to rewrite this as secant squared, and again, we're going to underline this second one because we're not going to mess with that. Then we can go ahead and replace this secant squared. We know that 1 plus tangent squared is the same as secant squared. So we get 1 plus tangent squared, secant squared d theta. Now we can do another u sub. I think we've used the letters u and theta and other stuff, so let's maybe do w equals tangent theta. dw is secant squared theta d theta. So that's going to be why we say that. That's going to be used up perfectly. This is a perfect substitution. And we get 1 plus w squared dw. Now, finally, we can integrate. Notice after all this, none of the steps have been integrating until right now. Everything has just been about manipulating the integrand. Now we are ready to integrate just using simple power rule. W plus 1/3 w cubed plus c. Now we can start unpacking. W was tangent theta, so tangent theta plus 1/3 tangent theta cubed plus c. Now we can go back to this substitution. We know that sine theta was equal to u. This is probably where we want to use that triangle. We'll put our right angle, put theta. label the sides. We know sine is your opposite over your hypotenuse. So again, we can think about this as, say, u over 1. So we can put the u as the opposite and the 1 as the hypotenuse. And then Pythagorean theorem will tell us that this will be 1 minus u squared. So what are we interested in? We're interested in tangent, which is your opposite over your adjacent. So we can then get this as u over square root 1 minus u squared plus 1/3 u over square root 1 minus u squared cubed plus c. And that's again just saying that each of those tangents is actually u over square root 1 minus u squared. Finally, we can go all the way back and say u is equal to ln x. So let's pop that in, and we get ln x over the square root 1 minus ln x squared plus 1/3 ln x over the square root 1 minus ln x squared, all cubed, plus c. So this is sort of the, I guess the finale in terms of an example, because what we actually did here is we sort of did a substitution into a trigonometric substitution into another substitution. Then we were able to integrate after all of that just by simple application of the power rule. Then we had to unpack all the substitutions and get back to this incredibly messy antiderivative. The key thing to think about here is that every time you do a manipulation, a trig sub, a u sub, an integration by parts, whatever, you always want to sort of reset and look at that new integral and say, okay, what am I going to do now? Not based on what I just did, but now that I have this new expression, what am I going to do? So it was sort of like about right here. We said, let's get rid of that ln x. Once we were here, though, we said, okay, I don't care that it was u equals ln x. This is irrelevant now. Now just look at this. What am I going to do from here? Then we decided on trig sub. Then after following the trig sub and simplifying, we got to here. And then we said, okay, new integral. What are we going to do from there? So every time you sort of use a technique, let your mind sort of reset and then say, okay, what am I going to do from there? Hopefully, after one, maybe two techniques, you can just directly integrate. But in this case, we had to do 3 different things. Eventually got to a very simple antiderivative in terms of just integrating, after all that hard work, just 1 plus w squared. All right, so this is going to wrap up our sort of discussion of techniques of integration. Notice nothing new was sort of presented in this section. It was just based on the techniques we had learned either from your Calc 1 class or from 7.1 through 7.4. This is more about putting those techniques in sort of synergy with one another and also learning how to strategize them. I highly recommend going through as many of the textbook exercises from section 7.5 as possible, as well as looking at the integration practice that you can find in the file section of Canvas. After this video, we'll be moving into section 7.7. We're skipping 7.6. It's not part of the syllabus of our class. So we'll be moving directly into section 7.7, which will change gears pretty completely and start talking about approximate techniques for integration. In other words, we'll learn some ways of approximating definite integrals without actually needing to perform all this integration.